The core concept of algorithm efficiency at its heart, algorithm efficiency refers to how well an algorithm utilizes computational resources, time and memory, to solve a problem. While correctness is essential, efficiency ensures that solutions work effectively even at scale. Poorly designed algorithms can lead to sluggish applications, excessive power consumption, or system crashes under load. Evaluating efficiency involves two primary metrics: time complexity and space complexity. These measures quantify how an algorithm's runtime and memory usage grow as input size increases. Understanding these concepts allows developers to compare algorithms and choose the most suitable ones for their use cases. Time complexity. Measuring computational workload time complexity describes the relationship between an algorithm's execution time and the size of its input. It's typically expressed using big O notation, which abstracts away constant factors and focuses on growth rates. For instance, an algorithm with O(n) complexity scales linearly with input size, while O(2 to the power of n) grows exponentially. To illustrate, consider sorting a list of numbers. Bubble sort has a worst-case time complexity of O(n superscript 2, making it inefficient for large datasets. In contrast, quicksort averages O(n log n, offering significantly better performance for larger inputs. Choosing the right algorithm based on time complexity can drastically impact application responsiveness. Big O notation represents upper bounds on runtime, helps predict scalability. Examples include O(1) O log n, O(n) O(n log n, and O(n superscript 2. Avoiding common pitfalls. Misunderstanding constants or ignoring asymptotic behavior can lead to overestimating or underestimating performance. Always prioritize dominant terms in complexity analysis. Space complexity. Managing memory usage while time complexity focuses on computation speed, space complexity examines memory requirements. An algorithm's space usage depends on both auxiliary storage, additional variables, and input data. For example, merge sort uses O(n) extra space due to temporary arrays during merging, whereas heap sort sorts in place with O(1) additional memory. Optimizing space complexity is crucial in environments with limited RAM, such as embedded systems or mobile devices. Techniques like in-place sorting, bit manipulation, and caching strategies can minimize memory overhead without sacrificing functionality. Trade-offs between time and space. Frequently, improving one aspect of efficiency comes at the expense of another. A classic example is hash tables versus binary search trees. Hash tables offer average O(1) lookup times but require significant memory for collision resolution mechanisms. Binary search trees provide logarithmic time complexity but may degrade to O(n) in unbalanced scenarios. Such trade-offs demand context-specific decisions. When working with constrained hardware, reducing memory footprint might outweigh minor gains in CPU usage. Conversely, in high-throughput applications, prioritizing faster operations could justify increased memory allocation. Practical strategies for algorithm optimization. Improving algorithm efficiency often involves identifying inefficiencies and applying targeted optimizations. One effective approach is code profiling, which pinpoints slow functions or loops through benchmarking and tracing tools. This enables developers to focus efforts where they matter most rather than guessing at potential issues. Another powerful technique is memoization, which caches results of expensive function calls to avoid redundant computations. Fibonacci sequence generation benefits immensely from this method, reducing exponential time complexity to linear by storing intermediate values. Memoization example: calculating factorials repeatedly can waste cycles unless cached results are reused across invocations. Data structure selection: using linked lists instead of arrays for dynamic collections reduces memory fragmentation risks, though access patterns differ significantly. Divide and conquer versus greedy algorithms. Some problems benefit more from certain paradigms than others. Divide and conquer splits tasks recursively until base cases are manageable, then combines partial solutions, a strategy seen in merge sort and matrix multiplication algorithms. Its strength lies in handling large-scale data efficiently, albeit with higher overhead from recursive calls. Greedy algorithms, on the other hand, make locally optimal choices at each step, hoping to reach global optimality. They excel in situations like Huffman coding or Dijkstra's shortest path algorithm but aren't guaranteed to find the absolute best solution for all types of problems. When to choose which paradigm? Selecting between divide and conquer and greedy approaches hinges on problem characteristics. If sub-problems overlap heavily, divide and conquer combined with memoization becomes ideal. However, for independent sub-problems requiring immediate decision-making, greedy strategies often suffice and run faster. For example, scheduling jobs with deadlines can be solved greedily by always choosing the job with earliest deadline first. But solving the traveling salesman problem exactly demands complex divide and conquer or dynamic programming techniques due to overlapping subproblems. Dynamic programming, overlapping subproblems and optimal solutions. Dynamic programming builds upon divide and conquer by recognizing repeating subproblems and reusing previously computed results. This avoids redundant calculations and transforms exponential time complexities into polynomial ones. Classic DP applications include the knapsack problem and edit distance calculation. The key distinction between dynamic programming and simple recursion is memoization, storing intermediate states so they don't need recomputation. This makes DP particularly useful in bioinformatics for aligning DNA sequences or in image processing for feature detection. Bottom-up approach *** starts from smallest subproblem sizes up to full problem scope, filling tables iteratively. Top-down with memoization *** uses recursion augmented with cache checks to skip unnecessary recalculations. Heuristics and approximation algorithms. Intractable problems, those lacking known polynomial time solutions, necessitate heuristic or approximation methods. Traveling salesperson problem variants fall here. Exact solutions are computationally prohibitive beyond small instances. Heuristics like nearest neighbor or genetic algorithms approximate good enough paths quickly. Approximation algorithms guarantee solutions within a bounded error margin relative to optimal answers. For example, Christofied's algorithm finds TSP tours within 1.5 times the optimal cost. Such guarantees allow developers to balance accuracy against feasibility for hard constraints. Balancing accuracy and speed. Choosing heuristics wisely balances precision with performance trade-offs. In logistics routing software, slight deviations from perfect routes save hours of computing time compared to exact solvers. Similarly, recommendation engines tolerate imperfect matches to deliver timely suggestions rather than waiting for precise rankings. However, misuse of heuristics can introduce subtle bugs. Developers must rigorously test approximations to ensure acceptable quality levels before deployment, especially in safety-critical domains like aviation navigation systems. Modern challenges in algorithm design. Contemporary computing landscapes pose new challenges for algorithm designers. Increasing parallelism via multi-core processors requires algorithms amenable to concurrency without causing race conditions or deadlocks. Parallel sorting implementations, such as parallel quicksort, distribute workload across threads but face synchronization overheads. Distributed computing introduces further complexity. MapReduce frameworks process massive datasets across clusters but demand carefully partitioned data to prevent bottlenecks. Selecting appropriate sharding strategies determines whether Hadoop jobs complete in minutes or days. Quantum computing implications. Rising interest in quantum computing threatens to redefine algorithmic efficiency standards entirely. Shor's algorithm can factor integers exponentially faster than classical counterparts, undermining RSA encryption security. Researchers now explore post-quantum cryptographic schemes resistant to such threats while maintaining reasonable performance on current hardware. Despite promising breakthroughs, mainstream adoption remains distant. Most enterprises still rely on traditional architectures, meaning conventional efficiency concerns persist alongside emerging opportunities presented by hybrid models integrating classical and quantum components. Caching and pre-processing techniques leveraging caching mechanisms smartly enhances apparent algorithm speeds. Operating system page caches hide disk latencies behind memory accesses, while browser DNS caching accelerates web requests. Application-level caching, like Redis stores, provides finer control over frequently accessed data. Pre-processing also plays vital roles in simplifying later computations. Pre-computing suffix arrays for string matching improves query response times dramatically. Normalizing databases ahead of queries prevents repeated normalization costs during runtime execution. Cache miss mitigation *** locality of reference principles suggest grouping related data together to increase hit ratios. Data compression *** reduces transmission/processing volumes, indirectly boosting overall throughput despite decompression overheads. Profiling tools and benchmarking practices. Effective optimization begins with accurate profiling. Instruments like Prof, Valgrind, and Intel vTune trace program flow, revealing hotspots consuming disproportionate execution time. These tools expose hidden inefficiencies masked by intuitive code logic. Benchmarking complements profiling by quantitatively comparing alternative implementations. Standardized test suites ensure fair comparisons across platforms. Micro-benchmarking isolates individual components, enabling fine-grained tuning of specific routines. Interpreting profiler outputs. Profiler reports usually show inclusive/exclusive timings. Inclusive counts include children calls, while exclusive focuses solely on the function itself. Identifying high exclusive time functions indicates prime candidates for optimization. Memory profilers detect leaks and bloat. Repeated allocations and tight loops suggest refactoring toward object pooling or reuse patterns. Stack traces pinpoint where memory was allocated, helping trace elusive leak sources. Best practices for writing efficient code. Writing clean, maintainable code doesn't necessarily equate to writing efficient code. Following best practices bridges this gap. Avoid nested loops whenever possible. Prefer vectorized operations using libraries like NumPy or SIMD instructions where available. Minimize conditional branches inside tight loops. They disrupt pipelining and cause branch prediction failures. Rearranging code to batch similar operations reduces branching frequency. Loop unrolling manually expands iterations to reduce overheads, though compilers often optimize automatically. Use built-in functions ***. Libraries implement optimized versions of common operations, e.g., sorted, custom sort. Early exit conditions ***. Return early from functions instead of letting full conditionals execute unnecessarily. Educational resources and learning pathways. Developers seeking deeper knowledge can follow structured learning paths covering algorithm theory, data structures, and advanced optimization techniques. Textbooks like Introduction to Algorithms by Corman et al. Serve as foundational references, while online courses on Coursera or edX provide interactive experiences. Practice platforms like LeetCode and HackerRank reinforce learning through hands-on problem-solving. Competitions such as ACM ICPC challenge participants to write highly efficient code under Prez community contributions and open source insights. Open source communities contribute immensely to advancing algorithm efficiency research. Projects like TensorFlow incorporate graph optimizations that reorder operations for better GPU utilization. Collaborative development platforms facilitate sharing of benchmarks and comparative analyses across implementations. Participating in forums, attending conferences, and reviewing peer-reviewed papers keeps practitioners updated on cutting-edge methodologies. Contributions to open source not only improve personal expertise but also advance collective knowledge benefiting future generations of developers. Conclusion: understanding algorithm efficiency is fundamental to creating robust, performant software. From grasping big O notation to mastering optimization techniques, this guide has explored numerous facets influencing algorithm selection and refinement processes. By continuously evaluating alternatives, leveraging profiling tools, and staying informed about evolving trends, developers can craft solutions that adapt gracefully to increasing demands. Remember, the goal isn't merely speed for speed's sake but achieving optimal performance aligned with business objectives and user expectations.